There was a time before stars. Not darkness in the way we use that word now, not the soft dark of a clear night with the Milky Way overhead, not the comfortable black between familiar constellations. That kind of darkness already contains light. It already contains the product of billions of years of stellar burning, the slow accumulation of hydrogen fused into helium, helium pressed into carbon, carbon into oxygen, all of it radiating outward across distances the mind cannot hold. The darkness before stars was something else entirely. It was a universe filled with matter and energy, but producing no light of its own. Hydrogen atoms drifting in enormous clouds, cooling slowly, not yet dense enough in any one place to collapse under their own gravity and ignite. The cosmos existed in a state that astronomers now call the cosmic dark ages, a period lasting perhaps 200 million years, possibly longer, during which the universe simply waited, cooling, expanding, growing quieter in every direction. And before even that, there was something stranger still. There was a moment, not a moment in the ordinary sense, not a second. You could have stood aside and observed when the entire universe was so hot and so dense that light itself could not travel freely. Photons existed, but they could not move more than a short distance before colliding with charged particles. The universe was opaque, not dark exactly, filled with energy, filled with radiation, but utterly unable to transmit a clear signal in any direction. Everything touched everything else instantly. There were no separate objects yet. There was no space in the way we experience it. That state lasted for roughly 380,000 years after the beginning. Then something changed. The universe cooled to a temperature of approximately 3,000 degrees. At that temperature, electrons and protons were finally able to combine into stable hydrogen atoms for the first time. The charged particles that had been scattering photons in every direction were suddenly gone, absorbed into neutral atoms, no longer available to obstruct the light. And in an interval that was brief by cosmic standards, the universe went from opaque to transparent. Light, which had been trapped for nearly 400,000 years, was suddenly free. It flooded outward in every direction simultaneously, not from a single point. From everywhere at once, from every location in the observable universe, a release of radiation that had been building since the very beginning finally moved without obstruction. That light has been traveling ever since, expanding with the universe, stretching as space itself stretched, cooling as it went, losing energy across the billions of years of its journey, until it arrived at the present moment as a faint signal hovering just a few degrees above absolute zero. That signal is still reaching us now. It arrives from every direction at once because it was released from every direction at once. It is called the cosmic microwave background, and it is the oldest light in the universe, not a metaphor for something ancient, but literally the oldest electromagnetic radiation that any instrument has ever detected. Everything you have ever seen, every photograph taken by every telescope ever built, every supernova and galaxy and planet and moon captured on any detector, all of it is younger than this light. Tonight we are going to follow that light back to where it came from. Not to a place exactly, to a time. To the universe as it was before it became the universe we know, before galaxies, before stars, before any of the structures that now fill the night sky had formed at all. The journey is a long one, measured not in distance, but in years. In the nearly 14 billion years that separate that first release of light from this quiet moment right now. The story begins in a state of almost unimaginable heat, and it ends with the faintest possible signal arriving at your location on this planet at this moment while you rest. To understand what the universe was before that light was released, it helps to let go of the idea of space as an empty container. We tend to imagine space as a kind of vast room, dark, mostly empty, with objects scattered through it at enormous distances. Stars here, galaxies there, and between them, nothing. That picture is useful for thinking about the universe as it exists now, but it does not describe the universe as it was in its earliest moments, and it actively misleads if you try to apply it to the period before the cosmic microwave background was released. In those first hundreds of thousands of years, space was not empty in any direction. The entire observable universe, everything that light has had time to reach us, from across nearly 14 billion years of expansion, was compressed into a region so small and so dense that every point in it was in direct thermal contact with every other point. Temperature was nearly uniform everywhere. Density was nearly uniform everywhere. There were no empty regions, no voids, no corridors of space through which a photon could travel unimpeded. What filled that space was a plasma. Plasma is the fourth state of matter distinct from solid, liquid, and gas. In a plasma, temperatures are so high that electrons cannot remain bound to atomic nuclei. They move freely, separate from the protons they would otherwise orbit. In the early universe, this plasma was composed primarily of hydrogen and helium nuclei, free electrons, and an enormous number of photons all interacting continuously. The photons could not travel more than a short distance before encountering a free electron and scattering, changing direction, exchanging energy, being absorbed and re-emitted in a new direction almost immediately. The universe, in this state, behaved like the interior of a star. If you have ever wondered what it looks like inside the sun, the answer is nothing. Not because there is no light, but because the plasma is so dense that photons scatter within fractions of a millimeter. The interior of the sun is bright in the sense of containing enormous amounts of radiation, but opaque in the sense that no single photon can travel any meaningful distance before being redirected. Light generated at the core of the sun takes tens of thousands of years to work its way outward to the surface, not because it moves slowly, but because it is deflected so many millions of times along the way. The early universe was like that, everywhere. This state is sometimes described as the photon epoch, or more simply, as the era of recombination, approaching a long period during which matter and radiation were locked together in a kind of intimate, turbulent union. Physicists describe the relationship between photons and matter in this period as being tightly coupled. The photons could not leave. The matter could not ignore them. Every part of the system influenced every other part continuously with no possibility of separation. And yet within that uniform, opaque, intensely energetic plasma, something was happening that would eventually give rise to everything. Tiny variations in density existed, not large differences, but small ones. A region slightly denser than average here, a region slightly less dense there. These variations were not random in the way that word usually implies. They had structure laid down in the first fractions of a second of the universe's existence by processes that physicists are still working to fully understand. The variations were small enough that the early universe looked nearly uniform from any perspective. But they were not zero. Those variations mattered. Gravity acts on density. A region slightly denser than its surroundings pulls matter toward itself slightly more strongly than the surrounding regions. Over time, over the long, slow expansion of the universe, following the release of the cosmic microwave background, those tiny density differences would grow. Matter would flow toward the denser regions. The denser regions would become denser still. Eventually, after hundreds of millions of years, the densest concentrations would collapse into the first stars. But that was still far in the future from where we are now. In the plasma era, those density variations were too small to see directly. They left their mark, however, on the radiation trapped within the plasma. The photons scattered not through a perfectly uniform medium, but through one with the faintest texture, slightly hotter here, slightly cooler there, by differences of roughly 1 part in 100,000. Those differences were imprinted on the radiation as it was released when the plasma finally cleared. They are still there now. Encoded in the cosmic microwave background, carried across nearly 14 billion years of expansion, is a map of those original density variations, not a perfect map and not a simple one to read, but a real one, the oldest dataset in existence. A record of conditions that no longer exist anywhere in the observable universe, preserved in the temperature fluctuations of a signal that has been crossing the cosmos since before any star ever burned. The plasma cleared because the universe kept cooling. As the universe expanded, its temperature dropped. This is a straightforward consequence of the physics of expansion. Spreading the same amount of energy across a larger volume lowers the energy density, which lowers the temperature. For the first 380,000 years, the temperature remained high enough to keep electrons free, to keep the plasma ionized, to keep the photons trapped. Then the temperature reached a threshold. At roughly 3,000 degrees, hydrogen atoms became stable. Electrons, which had been moving freely through the plasma, were suddenly captured by protons. Neutral hydrogen formed throughout the universe in what was, by cosmic standards, a brief transition, perhaps a few tens of thousands of years. And as the free electrons disappeared into atoms, the photons that had been scattering off them found themselves traveling through a medium that was suddenly, for the first time, nearly transparent. The light did not burst outward from a single source. It was released simultaneously from every point in the observable universe. Every location that had been part of the plasma became, at roughly the same moment in cosmic history, a source of freely traveling radiation. That moment is called recombination. The light it released is what we now call the cosmic microwave background. And the universe, newly transparent, newly cool enough for neutral atoms to exist, entered a period that had no light of its own at all. After recombination, the universe went dark. Not the dramatic dark of a sudden light being switched off, a gradual one. The cosmic microwave background radiation continued to fill all of space, but it was already cooling, already stretching toward longer and longer wavelengths as the universe expanded around it. Within a few million years of recombination, that radiation had shifted out of the visible spectrum entirely. There was no source of new light anywhere, no stars, no galaxies, no quasars, nothing that could produce photons in the wavelengths that matter, in the wavelengths that carry heat and drive chemistry and make things happen. The universe, for the first time, was genuinely dark in a way that had no predecessor. Astronomers call this period the cosmic dark ages. It lasted somewhere between 100 and 200 million years, possibly longer, depending on exactly when the first stars managed to form in sufficient numbers to begin changing the nature of the surrounding gas. During those hundreds of millions of years, the universe contained matter, enormous amounts of it, hydrogen and helium distributed across space in the pattern set by those original density variations, but nothing was doing anything with it yet. Gravity was working, but slowly. The slight overdensities that had been imprinted on the plasma before recombination were now free to grow without the opposing pressure of the radiation field. Before recombination, the photons had exerted pressure on the matter, pushing back against gravitational collapse. The tight coupling between radiation and matter meant that any region that began to contract would heat up and re-expand, like a compressed spring releasing. The density variations could not grow very large. They oscillated compressing and expanding in patterns that physicists describe as acoustic oscillations, like sound waves moving through the plasma at a significant fraction of the speed of light. When recombination happened, that pressure disappeared. The photons decoupled from the matter and streamed away freely. The matter, suddenly released from the opposing radiation pressure, was free to respond to gravity without interference. The overdense regions began to contract, slowly at first, then faster as more matter fell inward, deepening the gravitational well, attracting still more matter from surrounding regions. The Dark Ages were not static, they were a period of invisible accumulation. Hydrogen and helium were gathering into filaments and sheets, following the subtle gravitational scaffolding laid down before recombination. The overall distribution of matter in the universe was taking shape during these hundreds of millions of years, even though no light was being produced to reveal it. If you could have been present during the cosmic dark ages, which is not possible in any meaningful sense, but as a thought you would have experienced a universe expanding in all directions around you, filled with gas that was slowly, invisibly organizing itself into the structures that would eventually become everything. You would have seen nothing. There was nothing to see with. And then, in the densest concentrations of that gathering gas, something began to change. The first clouds of hydrogen, massive enough to collapse under their own gravity, had been accumulating for tens of millions of years. As they contracted, they heated. As they heated, the pressure inside them rose, but the mass was large enough, and the cooling mechanisms of the gas efficient enough in some regions, that the collapse continued despite the rising pressure. The gas fell inward. It spun. It fragmented into smaller, denser concentrations within the larger cloud. At the center of those concentrations, temperatures climbed. The numbers involved are large enough to be difficult to hold as images. A contracting cloud of hydrogen reaching temperatures of millions of degrees at its core, pressure rising until it crosses the threshold at which protons can fuse. One hydrogen nucleus pressing against another with enough force to overcome the electromagnetic repulsion between them and merge, releasing energy in the process. A tiny fraction of mass converted into radiation, in accordance with the relationship between mass and energy that had been true since the first moments of the universe. That release of energy pushed back against the collapse. The cloud reached a state of balanced gravity, pulling inward, radiation pressure pushing outward, a star. The first stars in the universe were not like the stars we see today. They formed from material that contained almost none of the heavier elements, carbon, oxygen, nitrogen, iron, that later generations of stars would produce and distribute through supernovae. The first stars had only hydrogen and helium to work with, the two elements produced in the first few minutes after the beginning. Without heavier elements to help radiate away heat, the collapsing clouds could not fragment as efficiently as later star-forming regions would. The result was stars of enormous mass. Some estimates suggest hundreds of times the mass of the Sun, perhaps more. Objects so large and so luminous that each one outshone entire galaxies of ordinary stars. They burned fast. A star many times more massive than the Sun does not live longer, it lives shorter. The more massive the star, the faster it burns through its hydrogen fuel. The hotter its core, the more rapidly it exhausts itself. The first stars may have lived only a few million years before exhausting their fuel and dying in supernovae of extraordinary violence. Those explosions scattered the heavier elements carbon, oxygen, silicon, iron that the stars had forged in their cores out into the surrounding gas. The next generation of stars formed from gas that was now, for the first time, seeded with elements beyond hydrogen and helium. That transition mattered for everything that followed. But the first stars had already done something else before they died. Their ultraviolet radiation was intense enough to ionize the hydrogen gas surrounding them. Neutral hydrogen, which had formed at recombination and persisted through the dark ages, began to be stripped of its electrons again by the light of the first stars. This process, called reionization, gradually transformed the intergalactic medium from a fog of neutral hydrogen into the ionized plasma it largely remains today. The universe became transparent again, not to the cosmic microwave background, which had already been traveling freely for hundreds of millions of years, but to ultraviolet light, to the light of stars and eventually galaxies, to the radiation that would make modern observational astronomy possible. The Dark Ages ended, not with a single event and not all at once. Different regions of the universe reionized at different times, depending on how close they were to the first sources of ultraviolet radiation. The process took hundreds of millions of years to complete, but the direction was clear. The universe that had been dark and filled with cooling gathering gas was becoming something new, illuminated, structured, beginning to resemble, at the very largest scales, the universe that instruments can now observe. The first stars burned in the dark for only a brief time before they destroyed themselves and seeded the next generation. But in that brief time, they ended 300 million years of silence. There is a good chance that at some point in your life, on some clear night away from city lights, you have looked up at the Milky Way without thinking about what you were actually seeing. Not the individual stars, the band itself, that soft, unresolved glow stretching from one horizon to the other, too diffuse to be a single object, too structured to be random. What you were looking at without any instrument was the combined light of hundreds of billions of stars too distant and too numerous to separate with the naked eye. Each one a sun, each one producing light through the same fusion process that began in those first enormous stars hundreds of millions of years before any of them existed. That band of light represents perhaps 10 billion years of stellar history. But the cosmic microwave background represents something older than any of it, older than the Milky Way, older than the first galaxy that ever formed, older than the first star that ever ignited. It is radiation from a time when none of those things existed yet, when the universe had not yet produced a single photon of starlight anywhere in its observable volume. For most of human history, no one knew it was there. The idea that the universe began in a hot, dense state, what we now call the Big Bang, was not widely accepted until the middle of the 20th century. Before that, competing models of the universe included steady-state theories, which proposed that the universe had always existed roughly as it appeared, with matter being continuously created to fill the gaps left by expansion. The debate between these models was not simply philosophical. It was a question that observations could, in principle, settle, and the cosmic microwave background, when it was finally detected, settled it. The detection was an accident. In 1964, two radio astronomers working at Bell Laboratories in New Jersey were attempting to use a large horn-shaped antenna originally built to communicate with early telecommunications satellites for radio astronomy. Arno Penzias and Robert Wilson were trying to measure faint radio signals from the outer regions of the Milky Way. To do this, they needed to eliminate every known source of noise from their instrument. They checked their electronics. They accounted for radio interference from nearby New York City. They even cleared a pair of pigeons that had been nesting inside the antenna horn and cleaned out what they carefully described in their notes as a white dielectric material the birds had deposited. The noise remained. It came from every direction equally. It did not vary with the time of day or the season. It did not correspond to any known astronomical source. It was isotropic, the same in all directions, which is an unusual property for almost any signal in astronomy, where most things come from specific locations. Penzias and Wilson could not explain it. They were not at that point looking for the cosmic microwave background. They were not even certain such a thing existed. At roughly the same time, a group of physicists at Princeton University led by Robert Dicke had been independently working out the theoretical prediction that if the universe had begun in a hot, dense state, there should be a remnant radiation field still present today, cooled by the expansion of space to a temperature of just a few degrees above absolute zero and detectable as microwave radiation, arriving uniformly from all directions. When Penzias and Wilson heard about the Princeton group's prediction, and the Princeton group heard about the Bell Labs observation, the connection was immediate. The noise that had resisted every attempt at elimination was not noise at all. It was the oldest light in the universe, arriving at the antenna from every direction simultaneously, exactly as the theory predicted. Penzias and Wilson had accidentally discovered the cosmic microwave background. They received the Nobel Prize in Physics in 1978 for an observation they had not set out to make, of a signal they had initially tried to eliminate. That discovery confirmed, more decisively than any previous observation, that the universe had a beginning, that it had once been in a state of extreme heat and density, and that it had been expanding and cooling ever since. The steady-state model, which had no mechanism for producing a uniform background radiation of this kind, could not accommodate the finding. The hot Big Bang model had predicted exactly this signal at roughly this temperature, decades before anyone found it. The discovery also opened a question that would take several more decades and multiple generations of instruments to begin answering. If the cosmic microwave background was uniform in all directions, What caused the universe to develop the structure it now has? A perfectly uniform early universe with no density variations of any kind would have expanded forever as a featureless gas, never forming stars or galaxies or anything else. The existence of structure of galaxies clustered into filaments and sheets, of voids hundreds of millions of light years across, of the entire observable universe, organized into a cosmic web, required that the early universe had not been perfectly uniform. The variations had to be there. The question was whether the cosmic microwave background preserved any record of them. The answer, it turned out, was yes. But seeing that record required instruments far more sensitive than anything available in 1964. The temperature variations encoded in the background, radiation, were tiny differences of roughly 1 part in 100,000 against an average temperature of 2.7 degrees above absolute zero. Detecting differences that small across the whole sky required decades of technological development and eventually the removal of the detector from Earth's atmosphere entirely. Ground-based instruments, operating through the absorbing and emitting layers of the atmosphere, could not achieve the required sensitivity. Balloon-based experiments came closer, but the definitive measurements required space. 3 satellites, across 3 decades, carried humanity's understanding of the cosmic microwave background from its initial detection to the detailed high-resolution maps that now exist. The first was COBE, the Cosmic Background Explorer, launched in 1989. COBE confirmed that the spectrum of the cosmic microwave background matched almost perfectly the theoretical prediction for radiation from a hot, dense plasma that had been cooling for nearly 14 billion years. It also detected, for the first time, the large-scale temperature fluctuations in the background, the faint imprints of those original density variations, present at the level of 1 part in 100,000, just as the theory required. The principal investigators of the COBE science team received the Nobel Prize in Physics in 2006. But COBE's maps were blurry by the standards of what the science demanded. The angular resolution was not fine enough to see the detailed structure of the fluctuations, the specific pattern of hot and cold regions, whose statistical properties encode information about the composition, geometry, and early history of the universe. 2 more satellites followed. WMAP, launched in 2001, produced maps of much higher resolution, revealing the detailed angular power spectrum of the fluctuations, with enough precision to constrain the major cosmological parameters: the density of ordinary matter, the density of dark matter, the geometry of the universe, the rate of expansion. Then Planck, launched in 2009 by the European Space Agency, pushed the measurements further still, producing the most detailed full sky map of the cosmic microwave background that has yet been made. What those maps revealed was not chaos. The fluctuations in the cosmic microwave background have a specific statistical pattern, a particular way in which the sizes and amplitudes of hot and cold regions are distributed across the sky. That pattern carries the imprint of the acoustic oscillations in the early plasma, the compressions and rarefactions of the radiation matter fluid that had been bouncing back and forth for 380,000 years before recombination froze the pattern in place. Reading that pattern, physicists found they could measure properties of the universe that no other observation could reach. The geometry of space itself, the total density of all matter and energy, the fraction of that density that consists of ordinary baryonic matter, the protons and neutrons and electrons that make up stars, planets, and people, the fraction that consists of dark matter, which interacts gravitationally but does not emit or absorb light, the fraction that consists of dark energy, the mysterious component, driving the accelerating expansion of the universe, all of it encoded in the faint temperature variations of light that was released 380,000 years after the beginning, the oldest message ever received. The pattern frozen into the cosmic microwave background is not arbitrary. It has a shape, a specific, measurable, mathematically precise shape that physicists can predict from first principles. and then compare against what the satellites actually observed. The agreement between the prediction and the measurement is one of the most precise confirmations of any scientific theory in the history of human inquiry. Not approximate agreement, not broadly consistent agreement, agreement to a level of precision that, in most contexts, would seem unreasonable to even attempt. To understand why that pattern carries so much information, it helps to return to the plasma, to that dense, hot, tightly coupled fluid of matter and radiation that filled the universe for the first 380,000 years. Within that plasma, the density variations from the very earliest moments of the universe's existence were not sitting still. They were oscillating. The overdense regions, slightly denser than their surroundings, therefore slightly hotter, would begin to compress under gravity, raising the local pressure. The increased pressure would then push outward, driving an expansion. The expansion would overshoot, creating a slightly underdense region, which would then begin to contract again under gravity. Compress, expand a wave, moving through the plasma at a speed determined by the physical properties of the fluid. That speed was roughly half the speed of light. Sound waves move through air at a speed determined by the density and compressibility of air. In the early universe plasma, the equivalent wave speed was far higher, not because the plasma was thin, but because radiation pressure was so dominant that it made the fluid extraordinarily stiff. These waves moved through the plasma of the early universe at a significant fraction of the speed of light, carrying the density variations with them as they traveled. For 380,000 years, these waves propagated. Then recombination happened, and the pressure supporting the waves vanished. The photons decoupled from the matter and streamed away freely. The waves stopped. Whatever compression or rarefaction each region of the plasma had reached at the moment of decoupling was frozen into the matter and into the radiation simultaneously. The matter retained the density variations as the seeds of future structure, the scaffolding on which galaxies would later form. The radiation carried away the temperature variations as the pattern we now observe in the cosmic microwave background. The waves had been traveling for a fixed amount of time, 380,000 years, at a known speed. This means there was a maximum distance that any wave could have traveled between the beginning of the universe and recombination. Regions separated by more than that distance could not have been in causal contact, could not have exchanged signals or influenced each other's density. Regions separated by less than that distance could have. That maximum distance is called the sound horizon. Its physical size at the time of recombination can be calculated from the known properties of the plasma, and its apparent size on the sky today, stretched by nearly 14 billion years of cosmic expansion to an angular scale of roughly 1 degree, is one of the most important numbers in modern cosmology. It is the characteristic scale of the fluctuations in the cosmic microwave background, the scale at which the acoustic oscillations were in a particular phase at the moment of decoupling, the scale that appears as a dominant feature in the statistical pattern of the temperature map. Physicists call this feature the first acoustic peak. When the WMAP and Planck satellites measured the angular power spectrum of the cosmic microwave background, essentially a measurement of how much variation exists at each angular scale across the sky, the first acoustic peak appeared at exactly the angular scale predicted by the theory. Then a second peak at a smaller angular scale, corresponding to waves that had completed 1.5 oscillations by the time of recombination. Then a third peak, then a fourth, a series of peaks and troughs, each one carrying information about the physical conditions of the early universe. The relative heights of these peaks tell physicists the ratio of ordinary matter to radiation in the early plasma. Ordinary matter baryons, the collective name for protons and neutrons, contributes mass to the oscillating fluid without contributing radiation pressure. More baryons make the compressions deeper because there is more mass to pull inward, and make the expansions shallower because there is more inertia to overcome. The The ratio of the first peak to the second peak in the power is spectrum sensitive to the baryon density, in a way that no other observation had previously been able to measure directly from the conditions of the early universe. What the measurements found was that ordinary matter makes up roughly 5% of the total energy content of the universe. 5%. Everything that can be seen, touched, measured directly, built from, burned, breathed, or assembled into stars and planets and people, all of it together accounts for 5% of what the universe contains. The rest is dark matter and dark energy, components that do not interact with light and whose fundamental nature remains unknown. Dark matter contributes roughly 27%. Dark energy, the component driving the accelerating expansion of the universe, accounts for the remaining 68%. Those numbers came, in large part, from reading the pattern frozen in the oldest light. There is something worth resting with in that. The most precise measurements of what the universe is made of did not come from studying what we can see directly. They came from studying the temperature variations in a signal released nearly 14 billion years ago, before any of the structures we can observe had yet formed. The composition of everything was encoded in the conditions of the plasma before recombination. The cosmic microwave background carries that encoding intact across the full span of cosmic history. Ancient civilizations mapped the sky with careful attention, noting which stars rose with the floods, which constellations marked the planting seasons, which patterns in the night served as a calendar more reliable than anything they could build on the ground. They were reading signals carried by light, using them to understand something larger than the light itself. The methods have changed so completely that the comparison seems almost absurd. But the basic action, receiving light from a great distance and reading from it, the structure of something you cannot visit, is the same one that has always connected human attention to the sky. The cosmic microwave background is simply the furthest that action has ever reached. The pattern in it also confirmed something about the geometry of the universe that had been theoretically preferred, but not observationally established. The angular scale of the first acoustic peak, that 1 degree feature on the sky, depends on both the physical size of the sound horizon at recombination and the geometry of the space through which the light has traveled since then. In a universe with positive curvature, like the surface of a sphere, parallel lines eventually converge, and distant objects appear larger than they would in flat space. In a universe with negative curvature, parallel lines diverge, and distant objects appear smaller. In a flat universe, the geometry of ordinary Euclidean space holds at the largest scales. The measured angular scale of the first acoustic peak matched the prediction for a flat universe. Space, at the largest observable scales, is flat, not curved into a closed sphere, not saddle-shaped and open. Flat to within the precision of the measurement, which is now very high. The total energy density of the universe is within a fraction of a percent of the critical value that produces flat geometry. Whether this is a coincidence or reflects some deeper principle operating at the very beginning of the universe is a question that remains genuinely open. But the flatness itself is not in question. The universe we inhabit, from the quantum scales of particle physics to the cosmic scales of superclusters and voids, exists within a geometry that follows the same basic spatial rules as the page you might draw a triangle on. The sum of its angles is 180 degrees. Parallel lines do not meet. The ratio of a circle's circumference to its diameter is pi everywhere and at every scale. That knowledge arrived in the data from a satellite measuring temperature differences of 100,000th of a degree in radiation that had been traveling since before the first star. The oldest light carried the shape of everything. There is a question that the cosmic microwave background raises quietly, almost without announcing itself. If the background radiation is so nearly uniform, the same temperature in every direction to within 1 part in 100,000, then the regions of the sky on opposite sides of the observable universe must have been at nearly identical temperatures at the time of recombination. they must have been in thermal equilibrium with each other. They must have exchanged enough energy to reach the same temperature. But they could not have. The observable universe, at the time of recombination, was large enough that regions on opposite sides of it were separated by distances greater than light could have traveled since the beginning. If nothing can travel faster than light, then no signal, no energy, no influence of any kind could have passed between those regions in the time available. They should have had no way to know each other's temperature. They should have been independent, uncorrelated, potentially very different from each other, and yet they were the same, not approximately the same, not similar in a way that could be explained by chance, the same to a precision that becomes increasingly difficult to account for the more carefully you think about it. Regions of the sky separated by tens of billions of light years, which could never have been in causal contact under any straightforward reading of the physics, have temperatures that differ by less than 1,000th of a degree. This is called the horizon problem. It is not a small puzzle easily set aside. It sits at the center of modern cosmology as a genuine challenge to simple models of the early universe. If the universe began in a hot, dense state and has been expanding ever since, at rates consistent with what we observe today, then the uniformity of the cosmic microwave background should not exist. The sky should be patchy. Different regions should have settled at different temperatures, reflecting the random initial conditions of regions that never interacted. Instead, the sky is smooth. The leading explanation for the horizon problem is called inflation. Inflation proposes that in the very earliest moments of the universe, not at recombination, not during the plasma era, but in the first tiny fractions of a second after the beginning, the universe underwent a period of extraordinarily rapid expansion. Not the gradual expansion that has characterized most of cosmic history, but an exponential acceleration so extreme that the observable universe inflated from a region far smaller than a proton to something approaching macroscopic scales in an interval so brief that no unit of time in ordinary use comes close to capturing it. If inflation happened, it solves the horizon problem directly. Before inflation, the entire region that would become the observable universe was small enough that all of it was in causal contact. Every part of it had time to exchange energy and reach thermal equilibrium. Then inflation stretched that region to an enormous size, preserving the uniformity that had been established when everything was close enough to communicate. The universe we observe is smooth because, before inflation, it was small enough to be smooth, and inflation locked that smoothness in place before anything could disrupt it. Inflation also explains the flatness. A universe with any initial curvature expanded by the extraordinary factor that inflation requires would have its curvature stretched to near zero, just as the surface of a balloon becomes locally flat when inflated to an enormous size. The flatness we observe is not a coincidence. On this account, it is an inevitable consequence of the expansion that inflation produced, and inflation makes a specific prediction about the pattern of density variations in the early universe. During inflation, quantum fluctuations, the unavoidable, random variations in energy that occur at the smallest scales in quantum mechanics were stretched by the expansion to macroscopic sizes. These stretched quantum fluctuations became the density variations that seeded all subsequent structure. The theory predicts that these variations should follow a specific statistical pattern across all scales nearly scale invariant, meaning that variations of similar amplitude exist at all sizes rather than being concentrated at any particular scale. The cosmic microwave background maps from WMAP and Planck confirmed this prediction. The pattern of fluctuations in the temperature map is consistent with scale-invariant initial conditions, stretched quantum noise, as inflation requires. Not perfectly scale-invariant, the measurements reveal a slight tilt, a preference for slightly larger variations at larger scales, but consistent with the theoretical prediction, to a degree that has strengthened confidence in the inflationary framework considerably. Inflation is not confirmed in the way that, for example, the existence of the cosmic microwave background itself is confirmed. It is a theoretical framework supported by multiple independent lines of observational evidence, but without the kind of direct, unambiguous detection that would settle the question definitively. Physicists continue to look for such evidence. The most promising avenue involves a specific type of signal in the polarization of the cosmic microwave background, a pattern called primordial gravitational wave imprints, or B-mode polarization, that inflation predicts should be present at a level that the next generation of instruments may be able to detect. That search is ongoing. What makes it worth describing here is not only the science, but the scale of what is being attempted. Physicists are trying to read, in the polarization pattern of the oldest light in the universe, the signature of quantum fluctuations that occurred in the first fractions of a second of the universe's existence. They are trying to detect in a signal that has been traveling for nearly 14 billion years, the imprint of events that happened before the universe was a second old. Events that produced the seeds of every galaxy, every star, every planet, every structure that has ever existed. The oldest light is being asked to testify about something older than itself. There is a version of this situation that is worth holding for a moment before moving past it. Every generation that has looked carefully at the night sky has found more than the previous generation suspected was there. The sailors who used Alpha Centauri for navigation did not know they were using a binary system. The who catalogued the Milky Way's stars did not know they were looking at one of hundreds of billions of galaxies. The engineers who built the first radio antenna to communicate with satellites did not know they were about to accidentally detect the remnant radiation of the beginning of the universe. Each layer of understanding revealed not a simpler picture, but a more layered one, more structure, more history, more connection between what was visible and what was not. The cosmic microwave background sits at the end of that sequence. Beyond it, there is no light. Not because the universe ends there, but because the plasma that preceded recombination was opaque. The cosmic microwave background is the surface of last scattering the boundary beyond which electromagnetic radiation cannot take us. We cannot see further back in time using light of any wavelength. What happened before recombination must be inferred from the pattern the plasma left behind, not observed directly. This is a genuine limit, not a temporary one that better instruments will eventually overcome. A fundamental one, built into the physics of how light and matter interact. The universe, before recombination, is in principle unobservable through any form of electromagnetic radiation. It can only be read through the imprint it left on the radiation it released when it became transparent, which is what makes the cosmic microwave background so quietly extraordinary. It is not just the oldest light, it is the last light from the only era of the universe we can never directly observe. Everything before it, the plasma, the inflationary expansion, the quantum fluctuations that seeded all structure, is accessible only through what this light carries. The universe handed us, at the moment of recombination, a single detailed record of everything that came before. A record written in temperature differences of 100,000th of a degree, stretched across the entire sky, arriving from every direction at once. We have been learning to read it for 60 years. We are still learning. Reading the cosmic microwave background requires more than measuring temperature. Temperature tells you how much energy arrived at your detector from a given direction in the sky. It is the most direct measurement, the one that COBE first made, the one that WMAP refined, the one that Planck brought to its highest current precision. The temperature map of the cosmic microwave background is the image most people encounter when they first learn about this radiation, a full, sky-oval projection colored in shades of red and blue. The red regions slightly warmer than average, the blue regions slightly cooler. The variations so small that the color scale has been artificially amplified to make them visible at all. But light carries more information than temperature. Light is an electromagnetic wave, and like all waves, It has a property called polarization, the orientation of the electric field oscillations as the wave travels. Unpolarized light has electric field oscillations in random orientations. Polarized light has them preferentially aligned in a particular direction. The cosmic microwave background is partially polarized because the scattering of photons off electrons in the plasma just before recombination preferentially produced polarization in directions related to the local temperature variations. Mapping the polarization of the cosmic microwave background across the full sky adds an entirely new layer of information to what the temperature map provides. Polarization patterns can be decomposed into two geometrically distinct types. The first type, called E-mode polarization, has a curl-free pattern. It looks like the field lines radiating outward from a point or converging toward one without any rotation. E-mode polarization is produced by the same density variations that created the temperature fluctuations, and it has been mapped with high precision by both WMAP and Planck. The E-mode signal confirms and refines what the temperature map shows, providing an independent check on the acoustic oscillation pattern and the cosmological parameters derived from it. The second type, called B-mode polarization, is different. B-mode polarization has a curl pattern field lines that rotate around points rather than radiating from them. Density variations alone cannot produce B-mode polarization to first order. The primary physical processes that generate B-mode polarization in the cosmic microwave background are gravitational waves ripples in the fabric of space-time itself. Inflation, if it occurred, would have produced gravitational waves along with the density perturbations. Those gravitational waves would have propagated through the plasma during the period before recombination, imprinting a faint B-mode polarization pattern on the radiation that was released at decoupling. Detecting that primordial B-mode signal would provide direct observational evidence for inflation evidence of a kind that the temperature map and E-mode polarization alone cannot provide. The challenge is extraordinary. The primordial B-mode signal, if it exists at the level predicted by the simplest inflationary models, is far fainter than the E-mode signal, perhaps 100 times fainter. It is also contaminated by other sources of B-mode polarization. Gravitational lensing of the cosmic microwave background by the large-scale structure of the universe converts some E-mode polarization into B-mode polarization. As the radiation travels toward us, polarized dust emission from within our own galaxy, tiny elongated dust grains aligned by the Milky Way's magnetic field, produces B-mode polarization that is orders of magnitude brighter than the primordial signal over much of the sky. Separating the primordial signal from these foregrounds requires measuring the polarization at multiple frequencies, building detailed models of the galactic dust emission, and achieving levels of instrumental sensitivity that push the limits of current detector technology. In 2014, a ground-based telescope called BSEP-2, operating from the South Pole, announced the detection of a B-mode polarization signal consistent with primordial gravitational waves from inflation. The announcement generated considerable excitement. If confirmed, it would have been one of the most significant observational results in the history of cosmology. It was not confirmed. Subsequent analysis, incorporating polarized dust emission data from the Planck satellite, showed that the signal detected by BSEP-2 was consistent with and likely dominated by polarized emission from dust within the Milky Way. The primordial gravitational wave signal, if present, was buried beneath the dust foreground at a level the observation could not distinguish. The announcement was walked back. The search continued. The current generation of B-mode experiments, including the BICEP array and its partners at the South Pole, the Simons Observatory in the Chilean Atacama Desert, and the planned CMB-S4 experiment, are designed with enough frequency coverage and sensitivity to characterize and subtract the dust foreground with far greater precision. They are looking for a signal that, if the simplest inflationary models are correct, should be detectable by instruments currently under construction or in early operation. Whether they will find it is genuinely uncertain. It is possible that inflation occurred, but produced gravitational waves at a level too faint for even the next generation of instruments to detect. It is possible that the B-mode signal will be found, and that its amplitude will constrain which of the many competing inflationary models best describes what happened in the first fractions of a second. It is possible that the search will return only upper limits, ruling out the simplest models and requiring theorists to explore more complex alternatives. Each of these outcomes would tell us something important. Science at this frontier does not only advance through confirmations. Precise upper limits are also data. Ruling out a class of models narrows the space of viable theories in ways that are genuinely useful, even when what is ruled out is something physicists had hoped to find. There is another signal in the cosmic microwave background that has already been detected, and that carries a different kind of information about the intervening history of the universe. As the cosmic microwave background photons travel toward us across nearly 14 billion years, they pass through the large-scale structure of the universe, the filaments, sheets, clusters, and voids of the cosmic web that formed from the original density variations after recombination. The gravitational fields of this structure deflect the paths of the photons, slightly a process called gravitational lensing. The deflections are small, but they accumulate over the enormous distances involved, and they leave a measurable imprint on both the temperature and polarization maps of the cosmic microwave background. Mapping the lensing signal in the cosmic microwave background provides a map of the total matter distribution along the line of sight between us and the surface of last scattering. That map includes dark matter, which does not emit light and therefore cannot be mapped by ordinary astronomical observations. The lensing of the cosmic microwave background is one of the most powerful tools available for studying the distribution of dark matter across the observable universe. Planck's lensing maps revealed the large-scale distribution of matter with a precision that complemented and extended what galaxy surveys had measured directly. The results were broadly consistent with the expectations of the standard cosmological model, the same model whose parameters had been constrained by the temperature and polarization maps, but not perfectly consistent. There is a tension in modern cosmology that has resisted resolution for over a decade, and the cosmic microwave background sits at the center of it. When the parameters of the cosmological model are fit to the Planck data, the temperature map, the polarization maps signal they predict a current expansion rate for the universe. That rate is expressed as a number called the Hubble constant, measured in kilometers per second per megaparsec. Roughly, how fast galaxies are receding from each other per unit of distance. The Planck data predict a Hubble constant of approximately 67.4 kilometers per second per megaparsec. Independent measurements of the Hubble constant, made using entirely different methods observations of Cepheid variable stars, used to calibrate distances to supernovae, which are then used to measure recession velocities at greater distances, consistently return a higher value, approximately 73 kilometers per second per megaparsec, sometimes higher. The difference is roughly 8 to 10%. In a field where measurements are now precise to a fraction of a percent, an 8% discrepancy between two independently derived values of the same quantity is not a rounding error. It is a problem. The discrepancy is called the Hubble tension. It has not gone away as measurements have improved. If anything, improved measurements have sharpened it, reducing the error bars on both sides, without bringing the values closer together. Either one or both sets of measurements contain systematic errors not yet identified, or the standard cosmological model is missing something, a new component of physics operating at some scale not yet incorporated into the model that affects either the early universe, changing what the cosmic microwave background predicts, or the late universe changing what the supernova measurements find, or both. What that something might be is one of the most actively discussed questions in cosmology at the present moment. The oldest light in the universe has led, through the precision of its measurement, to one of the sharpest unresolved puzzles in modern physics. That is not a failure of the method. It is the method working exactly as it should, returning results precise enough to reveal where the current understanding breaks down, pointing toward the next layer of the question that has always been there, waiting beneath the one that was just answered. There is a quality to the cosmic microwave background that becomes more affecting the longer you hold it in mind. It is not a source. It is not a thing in any particular place. It is a condition, a property of the universe itself, present everywhere, simultaneously, arriving at every point in space, from every direction at once. If you were anywhere else in the observable universe, orbiting a star in a distant galaxy, drifting in the space between galaxy clusters, somewhere in one of the great voids that separate the filaments of the cosmic web, the cosmic microwave background would still be there, still arriving from all directions, still at the same temperature, within the same tiny variations, still carrying the same encoded record of the plasma that released it. It is not a signal sent from somewhere else. It is what the universe itself looks like, from the inside, at the longest wavelengths and the greatest distances that observation can reach. That quality, omnipresent, ancient, arriving continuously from the edge of what can be seen, makes it unlike anything else in the observable sky. Every other thing astronomers study is located somewhere. A star is at a specific distance, in a specific direction. A galaxy has coordinates. A supernova occurred at a particular position, in a particular host galaxy, at a particular redshift, corresponding to a particular moment in cosmic history. Even the most distant objects, known quasars more than 13 billion light-years away, galaxies observed as they were, when the universe was only a few 100 million years old, are objects. Discrete things with locations. The cosmic microwave background is not located anywhere, or rather, it is located everywhere. The surface of last scattering, the region of the early universe from which the background radiation was released, surrounds us in every direction, at a distance of approximately 46 billion light-years, which is the current distance to the edge of the observable universe, accounting for the expansion of space since that light was emitted. We sit at the center of a sphere whose inner surface glows with the oldest light in the universe, not because we occupy any special position, but because the observable universe is defined by what we can see from here. An observer anywhere else would see themselves at the center of the same kind of sphere. The light released at recombination surrounds every point in the universe equally. There is something in that worth. Resting beside for a moment the idea that this ancient radiation does not favor any particular location. It arrived at Earth before Earth existed. It will continue arriving long after any instrument currently pointed at it has ceased to function. It was arriving at this location in space when it was empty gas, when it was a forming solar system, when the first simple chemistry was organizing itself in shallow water, when the first eyes opened and saw, for the first time, a night sky they had no framework to interpret. The light was already here. The question of what the cosmic microwave background will look like in the distant future has a quiet answer. As the universe continues to expand, the wavelengths of the background radiation will continue to stretch. Already shifted from the visible light it once was, when it was released, the plasma was at roughly 3,000 degrees, producing light in the near-infrared and red end of the visible spectrum into the microwave regime it occupies now, at a temperature of 2.7 degrees above absolute zero. As expansion continues, the temperature will continue to drop. The wavelengths will continue to lengthen. The signal will shift from microwaves into radio waves, and eventually into wavelengths so long that detecting them would require instruments of a size and sensitivity that nothing in the observable universe could practically build. In 1 trillion years, the cosmic microwave background will have cooled to a temperature so close to absolute zero that it will be effectively undetectable by any means we can currently imagine. A civilization existing in the far future, in a universe where the expansion has carried other galaxies beyond the observable horizon, would have no access to the cosmic microwave background as a source of information. They would not be able to measure the Hubble constant using the methods available to us. They would not be able to see the temperature fluctuations that encode the composition and geometry of the universe. They would live in a cosmos that had erased much of its own early history from the observable record. We exist at a moment when that record is still readable, not forever readable, not for much longer in cosmic terms, at the precision current instruments achieve. The window during which the cosmic microwave background is both present and accessible enough to yield detailed information about the early universe is not infinite. It is long by human standards, billions of years remain, but it is finite, and we happen to be living inside it. This is not a coincidence in the sense of something unlikely. It follows naturally from the fact that we are here at all complex chemistry and biology require the stable, temperate conditions that exist only during a particular era of cosmic history. And that era happens to overlap with the era during which the cosmic microwave background is still measurable. But knowing that it is not coincidence does not make the situation feel less particular when you sit with it. The instruments that have read this signal most precisely, Planck, WMAP, COBE before them, were built by people who spent careers learning how to measure temperature differences of 100,000th of a degree in radiation, arriving from the edge of the observable universe. The chains of reasoning connecting the raw data to the cosmological parameters are long and technically demanding, requiring careful modeling of instrument systematics, galactic foregrounds, secondary effects, and statistical uncertainties that took decades of methodological development to bring under control. And at the end of that chain of reasoning, what emerged was not complexity for its own sake. It was simplicity, a universe described by a small number of parameters fitting a coherent model, whose predictions match observations across an enormous range of scales and cosmic epochs. 5% ordinary matter, 27% dark matter, 68% dark energy, a flat geometry, a nearly scale invariant spectrum of initial perturbations, an age of 13.8 billion years, an expansion rate that is currently in tension with direct measurements in a way that may point toward new physics. Those numbers describe the universe we live in. They came, in large part, from a signal that Penzias and Wilson spent months trying to eliminate from their antenna, assuming it was noise, before learning it was the oldest light that exists. There is a generational thread in the history of this measurement that is easy to miss when the science is presented as a sequence of results. Penzias and Wilson detected the signal in 1964 without knowing what it was. The theorist who identified it worked at a different institution and learned of the observation through a phone call. The scientist who designed COBE spent years securing funding and managing the technical challenges of a space mission before the satellite launched in 1989, 25 years after the initial detection. The principal investigators of COBE, who received the Nobel Prize in 2006, had given decades of their working lives to a measurement that most of their contemporaries had considered either impossible or unnecessary when they began. WMAP launched in 2001, Planck launched in 2009, and operated until 2013. The scientists who designed Planck's detectors were, in some cases, the graduate students of the scientists who designed WMAP's detectors, who were, in some cases, the graduate students of scientists who had worked on COBE, or on the theoretical foundations that made the measurements interpretable. Each generation built on the previous one without being able to see where the chain would lead. The person who will design the instrument that detects primordial B-mode polarization, if such a detection is possible, may be in a graduate program right now, learning the techniques that will become the foundation of a measurement that does not yet exist, or they may not yet have been born. That continuity, generation to generation, each adding precision, each refining the question, each handing forward a sharper version of what remains unknown, is one of the quieter things encoded in the history of this measurement. Not in the data itself, in the human structure that produced the data. The light has been arriving continuously for nearly 14 billion years. The effort to read it has been ongoing for 60. Both will continue for a long time yet. Tonight the universe is 2.7 degrees above absolute zero in every direction. Not in some directions, not on average across a sample, in every direction simultaneously, to a precision that would have seemed like an unreasonable aspiration to anyone who first heard the signal accidentally coming through a horn antenna in New Jersey in 1964. The sky is smooth. The ancient light is still arriving. Nothing about that has changed tonight, and nothing about it will change in any way a human lifetime could measure. There is a particular kind of rest available in that. Not the rest that comes from resolution, from a question answered, a problem closed, a mystery explained and set aside. The Hubble tension is not resolved. The nature of dark matter is not known. The direct evidence for inflation has not yet been found. The physics of what happened before recombination, in the first fractions of a second, remains accessible only through inference. The questions that the cosmic microwave background has raised are, in several cases, sharper now than they were before the measurement was precise enough to reveal them. But there is a different kind of rest, the kind that comes from scale. When the full span of what the cosmic microwave background represents is held in mind, nearly 14 billion years of travel, from a plasma so hot and dense that light could not move freely, through the long dark ages before the first stars, through the ignition of those stars and their brief violent lives, through the slow assembly of galaxies and the gradual building of the cosmic web, through billions of years of stellar generations, each seeding the next with heavier elements, through the formation of a solar system around an ordinary star in an ordinary arm of an ordinary galaxy, through the long biological history of a planet that produced, eventually, instruments sensitive enough to detect temperature differences of 100,000th of a degree in radiation from the edge of the observable universe. When all of that is held as a single arc, the particular anxieties of any given night become very quiet. Not because they are unimportant, because they are small in a way that the scale of the universe makes gently, undramatically clear. First stars burned in darkness for only a few million years before destroying themselves in supernovae and scattering the elements that would eventually make everything else possible. They never saw what they made. They existed, they burned, they ended, and the universe continued without them, using what they had produced to build the next generation, and the next, each more chemically complex than the last, until stars were forming with enough carbon and oxygen and silicon and iron in their surrounding clouds to produce planets with solid surfaces and liquid water, and in at least one case, living things that would eventually look up and ask where everything came from. The answer was already in the sky, encoded in the faintest measurable signal, arriving from the edge of what can be seen, carrying the imprint of conditions that existed before any of the structures now visible in the universe had yet formed. The universe, at the moment of recombination, handed everything that would come after a record of everything that came before, a record written in temperature, carried by light, preserved across nearly 14 billion years of expansion and cooling until instruments existed that could read it. That record is not complete. The plasma era before recombination is, in principle, beyond the reach of electromagnetic observation. What happened in the first second, the first millisecond, the first fractions of a millisecond can only be inferred from the pattern left behind, not observed directly. There is a wall built into the physics of how light and matter interact, beyond which no telescope of any kind will ever see. But what is on this side of that wall is extraordinary enough. A precise mixture of ordinary matter, dark matter, and dark energy. A nearly scale-invariant spectrum of primordial fluctuations were consistent with quantum noise stretched to cosmic scales by an extraordinarily rapid expansion in the universe's first moments. An age of 13.8 billion years, a Hubble constant whose measured value disagrees with independent measurements in a way that may be pointing, quietly, toward physics that does not yet exist in any textbook. All of it read from light that has been traveling since before the first star. There is a version of tonight in which you are simply a warm living thing on a planet, orbiting an ordinary star somewhere in the middle of a galaxy that is itself somewhere in the middle of a local group of galaxies, which is somewhere in a supercluster, which is one small feature in a cosmic web that extends in all directions to the edge of the observable universe. From any reasonable outside perspective, you are at no particularly significant location. The universe does not organize itself around you, and yet the oldest light in the universe is arriving at your location right now, not at some other location, here. At this planet, at this moment, through the atmosphere and the clouds and the walls of whatever room you are resting in, photons that were released 380,000 years after the beginning, that have been traveling ever since, that passed through the dark ages and the era of the first stars and the long, slow building of galaxies, are completing their journey at this specific moment in time. They carry no message intended for you. The universe does not send messages, but they carry something, the imprint of conditions that made everything possible, the record of a moment when matter and light separated for the first time, the oldest information that the observable universe contains. It is arriving continuously. It arrived before you were born. It will arrive long after every instrument currently reading. It has gone quiet long after the questions it has raised have either been answered or replaced by deeper ones, long after this night has dissolved into everything else that has ever happened. The universe does not hurry. The light does not stop. Somewhere in the cooling dark, 380,000 years after everything began, a plasma cleared. Light moved freely for the first time. The dark ages followed, long and still, until the first stars ended the silence they were born into. All of it happened before any eye existed to witness it, before any instrument existed to measure it, before any mind existed to ask what it meant. The asking came later. The light was always already here. It remains.